Hello everyone. This class we continue to study Chapter 6, Section 1, the composition principle of integrated op-amp application circuit. Okay, let's look at the second part, integral and differential circuits. First, let's understand the integration circuit. Look at the circuit diagram on the right. Signal source Vs goes through resistor R, connect to the inverting input of the integrated op-amp. Inverting input of integrated op-amp. A capacitor C is connected to the output. The output terminal is grounded through the resistor RL, looking at the same direction input. The input terminal of the same direction is grounded through a resistor. This is the integration circuit. In this circuit, let's take a look at the inverting input of the integrated op-amp. Because of this reverse input can be viewed as a virtual disconnect. Therefore, the current I and the current IC on the capacitor can be considered approximately equal. And because of the two inputs of the integrated op-amp, virtual short circuit, that is, V plus and V minus are approximately equal. So we can think of the reverse input as a virtual ground. So the current I is equal to Vs minus 0 to R. In this case, I equals Vs2, since I is approximately equal to IC. So in this case, the voltage charged on the capacitor, we can ask for it. Assume that the initial voltage value of the current capacitor is 0. Then the charging voltage on the capacitor is in the opposite relationship with VO. Everyone sees that the charging voltage on the capacitor should be such a direction. What about the voltage difference across the capacitor? Since this side is a virtual ground, this side is VO. What about VO and this charging voltage? It is a relationship that the negative values equal. So VO is equal to negative C. Then the integrated value of the current IC at time t. This is VO's expression. Then, because IC and I are equal or approximately equal, then I can bring in this expression of I, which translates into this expression. Then we extract the R residence is 1 negative RC, multiplied by the integral value of Vs at time t. So you can see the voltage VO at the output is equal to 1 negative RC. Then multiply it by the integral value of Vs at time t. In this way, the voltage at the output is realized. Integral calculation of input signal voltage. Under normal circumstances, the voltage VO at the output should be equal to Vs integral value at time t, plus the initial voltage across the capacitor. The general integration circuit is used to convert the waveform. Then let's see, Vs hypothesis is a square wave signal. Then its voltage is constant at a certain moment. So the current I is also a constant current. If this current charges the capacitor, the voltage on the capacitor will also increase linearly. Therefore, the voltage VO at the output is a triangle wave of the same frequency. In other words, through the integration circuit, we can put a square wave signal like Vs into a triangle wave. Such output voltage signal realizes the waveform conversion. Let's look at the differential circuit again. What about the differential circuit? Let's take a look. Vs, input voltage signal, is connected to inverting input of integrated op-amp. A feedback resistor Rf is connected to the output. The input terminal of the same direction is also grounded through a resistor. The output is grounded via the load RL. This is a differential circuit. Here we take a look. It also integrates its input. Satisfy such a prerequisite of virtual short circuit and a virtual open circuit. Then if you consider the reverse input as a virtual disconnect, current I on the capacitor and current RF flowing through, the two are approximately equal. What is the current I equal to? Let's look at the current I, which is equal to Vs, the integral of time t multiplied by the capacitance value, because here can be seen as a virtual ground. Then this current is equal to C times the differential value of Vs times. So what does VO equal? VO minus the voltage at the inverting input is 0. It is equal to negative I times RF. Then this I is the differential value of Vs time. We can bring it in. So VO is equal to negative RF multiplied by C and multiplied by the differential of Vs. Therefore, the voltage at the VO input, then the differential operation of the input signal Vs, usually can also convert the signal waveform. Suppose the input signal Vs is a fixed frequency square wave. Then, after differential operation, the voltage at the output is VO. It becomes a pulse voltage, turned into a pulse at the point of saving, so it can be achieved, a conversion from square wave to pulse voltage. Let's look at the third part, logarithmic and anti-log operations. The picture on the right is application integrated op-amp, logarithmic operation circuit. Let's observe this circuit. Vs as input voltage source, connect to via RS resistor, inverting input of integrated op-amp. Between the reverse input and output VO, there is a transistor T connected. The transistor is actively grounded. Collector junction integrated op-amp, inverting input. The emitter is connected to the output of the integrated op-amp. The output of the integrated op-amp is grounded via the load RL. The input terminal of the same direction is grounded through the resistor R. This is a logarithmic operation circuit. Let's take a look. The current flowing through RS is defined as I. Then, I and IC are approximately equal. We have seen many times during the analysis. Inverting input of integrated op-amp can be approximated as a virtual disconnect. Therefore, I and IC are approximately equal. In this case, so what are I and IC? Since this is a triode T, electrode current of the triode, the relationship between it and its VBE voltage is IC is equal to its multiplied by E. VBE is raised to the power of VT. For the transistor, the electrode current and the voltage drop across its emitter satisfy such an exponential law relationship. Then IC is equal to I. What is I equal to? Because it can be seen as a virtual ground, so I is equal to Vs then Rs. That is, Is multiplied by E, VBE and VT is equal to Vs compared to Rs. We can derive from this expression. The VBE of E is higher than VT is equal to Vs then Rs times Rs. So what is VBE equal to? This is an exponential relationship. Then VBE is VT multiplied by ln Vs multiply Is by Rs. The expression of VBE is found. Let's see what a VO is for. The voltage at VO, it can be seen as a negative value of VBE on the triode. So VO equals negative VBE, which is equal to VBE equal to this expression. So VO is equal to negative VT times ln Vs, multiply Is by Rs. Finally, the voltage at the VO input, logarithmic operation of the input signal Vs is realized. This is the logarithmic operation circuit. Let's take a look at the anti-number operation, exponential calculation relationship. The figure in the upper right corner is an exponential circuit. Signal source Vs at the transistor emitter, the voltage signal as input. Transistor T is positive ground. The collector is connected at the inverting input of integrated op-amp. Between the reverse input and output of the integrated op-amp, with the resistor RF connected, grounding of the non-inverting input of the integrated op-amp. This is the exponential circuit. We can take a look. The transistor T inside, its current IC and its voltage VBE satisfy an exponential law relationship. IC is equal to Is multiplied by E. The power of VBE is greater than VT. Then there is VO. VO is voltage at the output. What does it equal? It is equal to IC. What defines IC in this direction? IC due to the inverting input of the integrated op-amp can be virtually broken. Therefore, IC and the current flowing through RF are approximately equal. Therefore, VO minus the voltage 0 here is equal to IC times RF. VO is the voltage drop across the feedback resistor. What about IC? It is an exponential rate relationship with VBE. We put this expression in. Then it is equal to RF multiplied by an exponential rate. Relation such an expression due to the voltage of the input transistor. VBE equals negative Vs. BE voltage and Vs are equal in sets and opposite in sign. So we make VBE equal to negative Vs. Bring it in to get VO. The negative Vs equal to RT multiplied by Is multiplied by E times Vt. In this case, the voltage VO at the output, then the exponential calculation of the input voltage Vs. This is the exponential arithmetic circuit. Okay, this lesson is over. Thank you.